So now that we've talked about some of the basic properties of electricity, we talked about voltage, we talked about what current was, talked about power, and we also introduced the idea of resistance. Let's actually start looking at some of how those elements can actually relate to each other, and then specifically how we can possibly break down these schematics in which we can actually find what we call equivalent resistances. So we probably talked about this right when we had our last meeting, but in order for us to understand what current is actually going to be driven from the source, we actually have to understand what that source, that voltage source, is actually going to see as far as the equivalent resistance within the circuit. For instance, if we personify ourselves as the voltage source and we're looking into the circuit, and let's just take this one right here before we even talk about the relationship of any of these elements. If we look into the circuit and we're thinking of ourselves as the voltage source and we're looking in, we actually don't see we wouldn't see the individual resistances of R1, R2, R3, nor would we see R1, R2, R3 in that manner, or even in this circuit right here, R1, R2, R3, or even R4. We actually, as the source, would only see one resistance, and that would actually be the equated resistance to basically these 2 points here. And the way we actually find that resistance is actually going to drive the value of charge that's actually going to flow out into the circuit. That current, that rate of change of that flow of charge is actually going to go into the circuit. Then we actually have to know how to equate all that resistance to that source. And there's a lot of other things that are going on with that current that's actually going to come out of the source, as well as how it's going to relate to voltages that are going to be applied across all these elements within the circuit. But we first have to understand the way that we can actually equate resistance to that source. And part of what allows us to do that is understanding truly what basically those elements' relation to each other really is. And it starts off really with two very, very basic building blocks that we really look at. First are basically series elements, and then the second are parallel elements. Series elements essentially are defined as simply two elements here exclusively sharing one point of contact. Okay, just one point of contact. And we can actually relate multiple elements being in series by seeing how all these are actually maybe separated by one single point of contact. So for instance, Vs here, our voltage source, is actually connected to R1, and they share an exclusive node. So that means only two elements here are sharing that point of connection. And if we look at R1 and R2 are exclusively sharing one single point of connection. R2 and R3 are sharing one single point of connection, and R3 and Vs are sharing one point of connection. So what that means is that Vs is in series with R1, R1 is in series with R2, R2 is in series with R3, R3 is in series with Vs. And we generally say that all of these elements here would effectively be in series. Now, even though Vs is not directly connected to R2 over here, because all these elements are effectively in series due to these relationship with these points of connection, then we can say effectively the whole loop right here is in series. Now, if you note here, I already went ahead and drew the points of connection. 4 points of connection here. I always suggest that you label, that's the first thing you should do when you start looking at any schematic, is to go ahead and label those points of connection up front. This is going to help you really be able to identify the relationships of those elements very, very, very quickly. So series elements, a couple of notes about them. They actually all share the same current, but have different voltages applied across them. And if they're sharing the same current, Going back to what we defined as voltage the other day, that was what? dWdq, okay, the amount of work that it takes to push that charge through. If they have the same charge flowing through them, then in that case, if these have different values of resistance, it's going to require different values of work. So in that case, different voltages that are actually going to be applied. So if we go around the closed loop though, if we look and I always like to draw equivalent resistance with basically an arrow looking in. On a test, I'm just going to say something simple as what would be the equivalent resistance seen by the source, in this case the voltage source. So series elements, all we have to do to find their equivalent resistance together is just add those total resistances. And sure enough, here we get Req, that's equal to R1 plus R2 plus R3. So series elements, we add those together. Now, another way that we can define those relationships is what we call parallel. And the most common mistake for students to make when we talk about parallel resistances is they start thinking about elements that actually physically look like they're in parallel. The definition of parallel elements is two or more elements connected together by two common nodes. And when we say common node, in this case, Vs actually is connected directly to R1 on two nodes at the top and the bottom. And we know that's connected to R1 with two nodes because right here, if we look, there is no other element on the top or bottom in between these two. And if there's no other element, then we just assume that's just a piece of wire and that resistance is negligible. If that resistance is negligible, then it won't have any effect on defining a node right here. So in this case, Vs is sharing two common points of connection with R1. R1 is also sharing two common points of connection with R2. And R2 is sharing two common points of connection with R3. So what this means is that Vs is in parallel with R1 and also in parallel with R2 and also in parallel with R3. Now the common way that we go ahead and combine parallel resistances together is basically 1 over the summation of the reciprocals of those resistance values. And this works for any number of elements. If I had 100 elements in parallel, it would be, well, that would be one heck of a calculation. But in this case, probably one of the things that you'll see in the book is this, is R1 times R2 over R1 plus R2. This is kind of the traditional way of looking at two elements in parallel and calculating those values. All this would be equal to 1 over R1 plus 1 over R2. This is the generalized form for equivalent parallel resistances. I do not like students necessarily using this, even though it's accurate for two elements in parallel. The common mistake that I see students do is that if we actually tacked over basically a third resistance here, then students sometimes come in and say, well, then we can also use this equation, and that's not right. That is absolutely not correct. So instead of doing what the traditional version of two elements being in parallel, the formula for that, R1 times R2 over R1 plus R2, instead of doing that, I just say keep one equation in your head or on your paper. You know, there's no reason to remember two equations that may or may not actually perform the same exact type of function. So just remember 1 over the summation of the reciprocals of those resistance values. And we can just call it good from there. I like having one equation versus two. So what we just talked about was simply two ways that we can actually define points of connection between resistive values and actually within any element within the circuit. Series, where we just have two elements sharing one common point of connection, and then also parallel elements where they share two common points of connection. So one thing that I would like to say is that it doesn't matter whether R2 is right next to R3 or R3 is next to R1. With parallel elements, what defines that relationship again is actually the points of connection. I could actually redraw the circuit where R3 replaces R1, and I move R1 over to this point where R3 sits. And if I redrew the circuit to look like that, that wouldn't change the circuit at all. At all. It would not change that circuit because the points of connection did not change. So we're going to continually see this as we go through examples, and especially when we get to things like how we actually divide current throughout the circuit. We're going to kind of maneuver, see how the physical relationship to these, whether R3 is next to R2 or R2 is next to R1, doesn't really matter. But how do we equate resistances together? Because when we have combinations of series and parallel elements, obviously these are very, very, very simple circuits here. R1, R2, and R3 in series on the left, R1, R2, and R3 in parallel on the right here. What if we actually have a combination of elements connected together in multiple manners? So there's a couple of ways, a couple of rules that we can just go ahead and follow that really makes going through and equating resistance very, very simplistic. The first thing, again, that you guys should do is label all nodes. Label all those nodes together. And from there, we combine the readily collapsible series or parallel elements. And then we start collapsing those elements from the opposite side of the source, and then start collapsing towards the source. So what do I mean by that? Here we have, let's actually look at the elements. So I got a point of connection here, point of connection here, and a point of connection here, and also here. So let's talk about how these elements relate to each other. First, we can see R3 is in series with VS, and that VS is in series with R1. However, if you look here at the top and the bottom, between R2 and R4, there is no other element. So it's just a piece of wire. So we could go ahead and say, well, R4 is connected directly to R2, and then R2 is also connected to R4 on the top as well. So what that means is that R2 and R4 are in parallel with each other. Let's also talk about the relationship, though. We can see that R4 is not only just connected to R2, but what would that relationship be to R3? Well, R3 cannot be in series with R2 because R4 is connected to it. And also, the only way that we could actually say the relationship of R3, R2, and R4 is just undefined. They're just connected. But right now, R2 is not in series with R3 or in series with R4. The only thing that we can say about relationships within this single circuit right here is that R2 and R4 are in parallel with each other, and that R3 is in series with VS, and that R1 is in series with VS. So we have to actually start readily collapsing basically elements that we can easily just go ahead and just say, well, they're immediately in parallel, immediately in series. We can go ahead and just break those down. And we're going to go through basically 3 examples of this so we can give you kind of multiple manners in which those elements could relate to each other. So if I wanted to actually find the resistance seen by the source, and that resistance is what would actually drive current out of that source itself, the first thing that we would absolutely have to do, because there's no way that we could actually combine any elements just yet towards the source other than looking at R2 and R4. R2 and R4 are definitely in parallel with each other, so that's the first place that we need to start, is go ahead and combine these two together, and what's going to happen is we're going to get an equivalent resistance, and that equivalent resistance is going to start relating now to R3 and R1. So let's actually take this circuit, let's actually apply some values to it, and let's see if we can start equating resistance towards the source. So, like I said again, we would actually have to start on the opposite side, and then actually start combining resistances to that source. So let's continue on the discussion. Let's go through some examples now. All right. So we're basically just going to take this circuit right here, and for the next couple of examples, we're going to just continually build on it. But let's start right here. So once again, we're just adding values to what we had over on the left-hand side of the board. I'm going to personify myself as the source. I'm going to look into this circuit right here. And I'm going to say, what resistance would we actually see? Well, and we're going to call that resistance seen by the source right there, REQ2, for equivalent resistance. But we saw earlier that the two resistors on the right-hand side were actually in parallel. They shared two common points of connection. So we could combine those together in terms of their equivalent resistance. They're in parallel, and so I went ahead and redrew the circuit down here. I always say each step that you go through and draw your, start equating resistance, go ahead and redraw that schematic, because eventually it's going to help you having a map of how these resistances were equated basically down the line. So in this case, REQ1, which is what I defined as a parallel relationship between 20 and 30. REQ1 is equal to 1 over the summation of 1 over 20 plus 1 over 30. And that gave us 12 ohms. And so that combination of parallel equivalence of 12 ohms, this 12 ohm resistance, that equivalence, now becomes in series with 10 ohms and also becomes in series with this 12 ohms down here. Because 10 and the equivalent resistance here shares one single point of connection, and it also shares one single point of connection down here with this 12 ohm resistor. And so by that notion, the resistance that would actually be seen by the source, we would just have a single series loop. We can go ahead and combine the remaining resistances in series with REQ2. So 10 plus 12 plus that equivalent resistance gives us 34 ohms. 10 plus 12 plus 12 gives us 34 ohms. And so that 34 ohms would actually be what would drive current coming out of this source right here. Not necessarily, it wouldn't actually be what drives current, but it would help determine the value of current that would actually flow out of that source. So, again, all we had to do was say, well, we can't actually combine 10 with 20, can't combine 20 with 12, so we have to look further over to the right, and sure enough, 20 and 30 were in parallel with each other. Combine those two together, and once they're combined in parallel, that equivalence becomes in series with 10 and also becomes in series with 12. And so we just combine the remaining three elements together, we're done. What if, though, we build upon the right-hand side here? Let's see what we can do. Well, I went ahead and just said, why don't I just go ahead and just, instead of having a 30 ohm resistor on the right-hand side, why don't I go ahead and say, well, what if I put two elements together in series? What do I do with that? Well, let's look at the circuit first. So sure enough, by these points of connection, Vs is connected to 10 in series, Vs is connected to 12 in series. Here, we got still our 20 ohm resistor, and it's going to share a common point of connection with the 40 up here. There's no other element in between still. And down here, that 20 is connected to 15 because there's no other element there either. It's just a piece of wire. But what about 40 and 15 together? Well, looks like 40 and 15 are actually sharing a common point of connection. So that means that they would actually have to be in series with each other. But let's just go through and make sure that we know what we can and cannot combine readily. Well, I can't combine 20 and 40 because they're not in parallel right now. And 20 is not in parallel with 15. 20 is not in series with 12 because you got another connection over here. Remember, only two nodes allow for, two elements exclusively sharing one node can be in series. And also 20 is certainly not in series with 10. We can't combine any of those. So we have to start over here, and the only thing that we can actually combine at this point actually would be 40 and 15 together. So we combine those two together, we get 55. So that equivalence then becomes in parallel with 20. Let me just redraw this for you guys, just to make sure that we see it. I thought I had redrawn that again, but apparently not. So all we have to do is draw an extra schematic. Yeah, let's just go ahead and do that. So once we combined 40 and 15, I think you guys are going to see that that equivalence of REQ1 became in parallel with 20, because sure enough, those are two common points of connection. So now we can actually go through and combine the equivalent resistance with that 20 ohm resistor. And I'm going to call that REQ1. And so sure enough, 1 over the summation of those, so that's 1 over 20 plus 1 over the series relationship of 40 plus 15, which is what we showed right here. And so that becomes 13.84 ohms. So once we actually combine 40 and 15 together, that gives us 55, and then we go ahead and combine that in parallel, that equivalence in parallel with 20, then that equivalence of REQ1 becomes in series with 10 and also in series with 12. So all we have to do to find REQ2, which is what we're, that's the resistance we're personifying as being seen by us looking into the circuit. So sure enough, REQ2 becomes 10 plus 12 plus 13.84 ohms. That gives us 35.85 ohms. So you guys should be seeing a little bit right now that sure enough, the only thing that we could combine readily was 40 and 15 together into 55 ohms. But it's that combination that now becomes in parallel with the 20. Let's see if we can expand a circuit like this just a little bit more and make it a little bit more complex. Because what you're seeing so far with these two examples is that we're just looking on the right-hand side and we're collapsing it down towards the source. Sometimes we may have connections towards the source that we may be able to combine readily up front as well. Let's take a look. So all I did was take the 10 ohm resistor and I tacked on a 20 ohm resistor up here. And I took that 15 ohm resistor and I tacked on another 30 ohm resistor. Let's see about the nodes here. And by this time, you guys should start being able to recognize the nodes pretty readily. Well, sure enough, 12 is still connected to VS in series. However, VS is not in series with 10 anymore, because now we actually have a 20 ohm resistor that's connecting down to that 10 ohm. There's no element in between each of these portions here. And so sure enough, 10 is now connected to 20 on the right-hand side as well, but oh, look at this. Here 20 is connected to 40, there's no element in between, and also connected to 10 to 20 and also 10. So now we got 4 elements connecting right here. Let's take a look right here too. 20 is connected to 15. Oh, because there's no other element in between here too. It's also connected to that 30 ohm resistor. So if we look at series and parallel relationships, the only resistances that are actually in parallel with each other are actually going to be 15, 30, but also we have 10 and 20 in parallel over on the right-hand side. Note too that 15 is no longer in series with the 40 ohm resistor because we put this 30 ohm resistor in parallel with it. And because of that, that killed that relationship. 40, 15, and 30, that point of connection that's connecting all 3 of these together is just undefined. That we don't have to define it as series or parallel, it's just undefined. So what could we readily combine? Well, looking back and thinking about looking out into the circuit, 15 and 30, they're in parallel, we could go ahead and combine those. And that combination would then become in series with the 40 ohm resistor. We can also readily combine 10 and 20. Combining 10 and 20 here would actually not hurt an order of operations in terms of breaking down resistances within the circuit. Because they're in parallel here, we can go ahead and readily combine those two together. And so if we combine 15 and 30 together, I usually say that, as we start going down through lectures, you're going to see me do this a lot more. I denote parallel relationships with 2 literally parallel bars, vertical parallel bars. So 15 in parallel with 30 is 1 over 15 plus 1 over 30, and that gives us 10 ohms. And then REQ2, which is a 10 and 20 in parallel with each other. Sure enough, 10 in parallel with 20. equals 1 over the summation of 1 over 10 plus 1 over 20, which gives us 6.67 ohms. So now we redraw the circuit. And if I redraw the circuit, oh, look at this. 40 now becomes in series with the equivalent resistance of 10 ohms, which is what 15 and 30 was together combined. So these two become in series, and then also here we got 6.67, and now that looks like that's become in series with VS. So this looks very, very, very much like the prior example. And because of that, we know exactly what we need to do. We first need to, the only thing that we can do at this point is combine 40 and 10 together in series with each other. And so when we do that, that becomes 50 ohms, and that combination then shares two common nodes with 20 ohms. And so we can go ahead and combine those together in parallel. That comes out to be 14.29 ohms. So 14.29 ohms then would actually become in series with 12. It would share a single common point of connection with 12, and also share a single common point of connection with 6.67 ohms. So 6.67 becomes in series with 14.29, becomes in series with 12, because they're all effectively in series with each other. And I say effectively, once again, we talked about this, because 6.67 is directly in series with 14.29. 14.29 is directly in series with 12, but 6.67 is in 14.29, and 12 are effectively in series with each other. Because even though 16.67 is not directly connected to 12 in series, because of this guy in the middle here, that basically holds that connection together of that series relationship. So in this case, the final resistance that would be seen by that source would be 6.67 plus 14.29 plus 12, which gives us a total resistance seen by that source of 32.95 ohms. So just in summary, the absolute first thing that you should do when you see any circuit right now is go through and label all the resistances, and from there, go ahead and see what readily collapsible series or parallel relationship exists, and then start on the opposite side of the circuit where we're actually, from where we're looking for the equivalence, and start breaking down towards the source. And as you do those equivalent resistances, redraw your circuit. Once we actually start looking for voltages and current throughout the circuit, you're going to see that actually having that essential map right at your hands will actually help you see how currents and voltages will eventually divide. So, trying to set you guys up for success. Yes, I will ask you guys to be redrawing these circuits on test so I can actually see what you're doing. It will help me give you guys more partial credit, but I assume you're going to do everything correct the first time. But anyway, please let me know if you have any questions. We're going to be practicing this and throughout more examples that we see within our teams meetings, and in other classes we're going to see, basically these elements and their relationship. We're going to talk about them continuously so that you guys are gaining plenty of experience in looking at these schematics up front. So I'll see you guys next time.